In this mini lecture, we're going to talk about the output power of a force. A force that does work transfers energy, and the rate at which this force transfers energy is the output power of that force. So we can write the power in this way. The output power of a force is equal to the work done by that force over the time period. And remember, we can also write work as a force applied over some distance. So we can write the work as the force times the displacement over the change in time. And we can sort of pull out that F there. So we have the force times delta X over delta T is equal to power. And what is delta X over delta T? That's change in position over a change in time. That is a velocity. So you can also write the power as being a force times a speed. So this, a definition for power equaling force times speed, is the rate of energy transfer due to a force acting on an object moving at some constant velocity here. We need a constant force and a constant velocity to make this equation here work. So power equals our work over the change in time, which is equal to the force applied through some distance over the change in time, which is also equal to the force applied times the speed at which that object is moving, which is subject to that force. That force applied is causing the object to move at some constant speed v. Okay, so those are a couple of definitions that we can use for power, and we're going to use them in a couple of different ways to solve some problems. The units of power are units of watts. 1 watt is equal to 1 joule per second. Remember that our unit for work was also a joule. We're dividing it by a time. So the power has to be a joule per second, or we also call that a watt, W-A-T-T. So with that explanation, okay, we've got power is equal to work over time. We've also got power is equal to force times speed. We're going to use this in a couple of different ways to solve some problems. The first one we're going to do is here. This is going to be your engagement check for this video, okay? So you have 4 different students who are running up the stairs in some time shown here. They're running up the stairs. They go up some vertical distance, either 20 meters or 10 meters for these. Which student has the largest power output of these students? Well, how are we going to think about the power? We had a couple of different definitions. Well, let's use for this one, power is equal to the work that this student does over the change in time. We are going to think about the work that this student does against gravity over the change in time. So I'll show you with my little iPad here how you can calculate which student is doing the most amount of work. Our power is equal to a work over change in time, okay? It's also equal to the force applied at some speed. We're going to use this next formulation, power equals force times speed, in another problem. For this problem, we're going to think about power is equal to a work over time. The work that this student does is work against gravity. So let's see, work is our force times the distance over delta t. And so the force that they're moving against gravity is their weight. So the weight of these students is their mass times gravity, okay? And the distance over which they're moving that weight is a vertical distance, okay? That's the work that they're doing against gravity, okay? And so our distance then is just going to be the height that we move vertically, okay, for our power. So we divide that by the change in time. So for each one of these students to find the power output of themselves, which is the work that they're doing against gravity to move themselves upward along the stairs, divided by the change in time. Okay, so you're given the weight or the mass of each one of these students. You know the acceleration due to gravity. You're given the height, the vertical height over which these students move themselves against gravity, and you see the change in time. So you can calculate this quantity for each one of those students, A, B, C, or D, in order to figure out what the power is that they are outputting as they're running themselves up the stairs. And so then you can compare those powers for all those students to figure out who has the greatest amount of power output, who has the least amount of power output. And you're going to rank them in order from the greatest to the least amount of power output. And then we're going to use the other formulation for power. Power equals our force times speed. We're going to use that power expression in order to figure out the power delivered by an elevator motor.
We are going to use our concept of power and combine it with Newton's second law in order to solve this problem here. We have a 1,000 kilogram elevator which carries a load of 800 kilograms. So the sum total of the mass of my elevator plus the people inside it is 1,000 kilograms plus 800 kilograms. There's a constant friction force of 4,000 newtons that's retarding the motion of this elevator as it is pulled upward by the elevator motor. Okay, so this elevator is connected by a cable to a motor. The motor is pulling that cable up. Okay, so the motion is up and it's pulling it upward at a constant speed of 3 meters per second. What do we remember about constant speed? If the speed is constant, that means that the acceleration is 0, because acceleration is our rate of change of velocity. So if velocity is constant, then our acceleration is 0 meters per second squared. Okay, so our question is, what minimum power must the motor deliver to lift this fully loaded elevator at a constant speed of 3 meters per second? Okay, well, let's just start by thinking about the power that we need. Okay, there are two ways we can write our equation for power. Two ways. But the way that we're going to use it here is we're going to use this formulation that the power is equal to the force applied times the constant speed at which that force is applied. Okay, so there's power is equal to work over time, or power is equal to energy over time. We're going to use this one. Power is equal to force times constant speed. Well, we've got a constant speed here. We can figure out the force that our motor is applying in order to raise our entire cable, in order to raise our entire elevator upward. So we're going to use this formulation for power. Okay, so we know already the constant speed at which that motor is pulling upward on that cord width to move the elevator up. That's 3 meters per second. What is this force right here then? Well, the force the elevator motor must deliver is through the force of tension in the cable. So if we can figure out the force of tension in this cable, then we know what force our motor has to be exerting in order to move everything up at this constant speed. Okay, so to figure out what that tension force is, well, I guess the first thing we should do is draw our free body diagram of the elevator. So we represent our elevator mass here as that dot. We have the weight of everything in that elevator, the elevator itself plus the person. So we've got, I'll call it M1 plus M2 times gravity. It's the weight of that whole system here, okay? And we also have the force of friction that's acting opposite our direction of motion, and that's our 400 newtons, okay? And then we have the tension force pulling upward, okay? And remember we said that the force the elevator motor must deliver is the same as this tension force in the cable on the elevator. Okay, so these are the same. So what we're going to do is use Newton's second law in order to figure out what this tension force is. We can do that by the sum of all of our forces in the vertical direction must equal our mass times acceleration in the vertical direction. But where we said we're traveling at a constant speed, which means that we have no acceleration. So this right-hand side of the equation is 0, equals 0. And so we have our tension upward. We've got the weight of our objects downward. And then we have the friction force that is also impeding this motion. Okay, so the weight and the friction force were pointing downwards, so they get a minus sign in front of them. So if I solve this for tension, tension is equal to the friction force plus mass 1 plus mass 2 times gravity. Okay, so that's 400 newtons plus my 1,000 kilograms plus 800 kilograms. That's 1,800 kilograms times 9.8 meters per second squared. Okay, so then my total tension force is 2.16 times 10 to the 4 newtons. Okay, so I take that tension force and I plug it in here for the force that my motor must deliver in order to raise up this entire elevator at a constant speed. That equals 2.16 times 10 to the 4 newtons times my constant speed of 3 meters per second. And that gives us a power of 6.49 times 10 to the 4 watts of power that this motor must deliver in order to raise up that elevator and its passengers at a speed of 3 meters per second.
Here's another way we can express power. Power can be thought about as a rate at which energy is expended or supplied. Whenever we think about power, electrical power, your energy company is charging you for the energy you use, the total amount of energy you use. They take this equation and they rearrange it. So they will write your energy bill in terms of kilowatt hours. They're finding your energy expenditure in kilowatt hours. So if we solve this problem for energy, power is equal to energy use over time. Solve it for energy. Energy is equal to the power times time. So if our power is in units of watts, our time here, we could put it in units of hours. So you could find your energy use in terms of the power that's being supplied to your house with electricity times time. Next semester, we're going to learn about how you can calculate the power associated with a circuit or with an electric current. Our body converts food into energy, and we can calculate the power consumed by different bodily functions and by different organs. This is a chart from your textbook. So our body takes food energy and it converts it into the work that we do to move ourselves around during the day. It converts it into thermal energy to keep us warm, and it converts it into, well, stored fat. We got to store some of that in case of the future. Okay, so here's a chart that shows the power consumed by different body parts just by us sitting at rest. This power that our body consumes is also related to our oxygen consumption. So the more oxygen we're consuming, the more power our body's also consuming. So you can measure a person's oxygen consumption rate and equate that to how much power their body is expending. Well, we're going to do another problem here to think about power equaling and energy over time, energy consumption over time. And we're going to think about that by thinking about the energy in a Big Mac and how much work we have to do in order to burn off all of the energy stored in that Big Mac that our body just consumed. Okay, so a Big Mac has 33 grams of fat. 1 gram of fat is about 39,000 joules. Okay, so 1 gram of fat has about 39,000 joules. It contains energy, okay, that our body is going to consume. How many joules of energy are stored then in our 33-gram Big Mac, okay? So we have a conversion factor here. 33 grams of fat inside our Big Mac. We multiply that by the fact that we know that in 1 gram of fat, there's 39,000 joules of energy, okay? So I'll take 33 times 39,000. That tells us that one Big Mac contains 1.29 times 10 to the 6 joules of energy for our bodies. Okay, so when we're solving problems related to energy, you can compare that to the energy stored in a Big Mac. That's a lot, okay? 1.29 times 10 to the 6 joules. Now for part B, how many kilocalories is this? 1 kilocalorie, which we call kcal, is equal to 4,184 joules. Okay, so when you look on the back of food labels, and you all I'm sure have done this, it shows you the calories in that food label. So if you look on the back of a Snickers bar, you can see how many calories are in there. Okay, so on food labeling, what you see as the calorie on the back is actually a kilocalorie. Okay, so if you, let's see, the granola bar that I eat sometimes in the morning is 120 calories. So that's 100, it says calories, but it's actually 120 kilocalories. And if I take that and I multiply it by 4,184, that tells me joules, that tells me how much energy is stored in that granola bar, okay? So let's see. So how many kilocalories is this 33 grams of fat? So we take our 1.29 times 10 to the 6 joules, and we multiply it by another conversion factor. And that conversion factor is, there's 4,184 joules in 1 kilocalorie, okay? The joules cancel. So that tells us that 33 grams of fat is the same thing as 308 kilocalories, okay? So, or that would be the calorie content that you would see in like food labeling package. So the Big Mac, just from the 33 grams of fat, contains 308 kilocalories, or what we normally think about as calories when we're consuming food, okay? That's just from the fat. That doesn't count the carbs that are in, you know, the bread that goes along with the Big Mac, okay? So that's just from the fat. Now, how much stair climbing is required to work off the energy from just the fat in this Big Mac? Okay, it might make you a little bit sad. Maybe not. It just depends on, you know, how much effort you put into your exercise. So we want to find how much stair climbing do we have to do to work off this 33 grams of fat. We're going to assume that the average human expends 385 watts of energy climbing stairs. So how much stairs do we have to climb in order to work off this 33 grams of fat? Well, to think about that, we're going to start by power. Power is equal to our energy consumption over time, okay? So how much stair climbing, let's think about maybe how long it would take us, how many hours it would take us to climb these stairs to work off this fat. So if we solve this equation for time, time is equal to energy over power. Okay, so the energy we have to get rid of, this energy from the fat that we've consumed, we have to expend in order to sort of get it out of our bodies, okay? That energy is going to be the 1.29 times 10 to the 6 joules that we found up here, the energy stored in our 33 grams of fat. And then we have to divide it by some power consumption, a power consumption of our bodies. And so there's a chart in your book. This is just where I got this information from. One human expends on average 685 watts of power climbing stairs. So if we divide this energy by power, we find the time that it takes us to climb the stairs in order to burn off the 33 grams of fat from the Big Mac. The time it takes us is 1.88 times 10 to the 3 seconds, okay? And so if I want to convert that into hours, 1.88 times 10 to the 3 seconds times, in 1 hour, there's 3,600 seconds, okay? So if I divide 1.88 times 10 to the 3 by 3,600, that gives us 0.52 hours. So to burn off those 33 grams of fat from our Big Mac, we'd have to climb stairs for, oh, I see that it's chopped off there. We'd have to climb stairs for 0.52 hours or 30 minutes in order to just burn off the energy from the 33 grams of just the fat in our Big Mac.